Good afternoon, everyone. This is Group 7 CDR presentation for our project My Plant. Here we can see our team consists of 5 engineers, which consists of 3 electrical engineering and 2 computer engineerings, with Max being an electrical engineer, Bannon being an electrical engineer, Kyle being an electrical engineer, Berkai being a computer engineer, and myself, Raphael, a computer engineer. Motivations and backgrounds. While we thankfully knew each other due to previous classes taken together, this is our first time working together as one for a major project. So we of course had some problems arise during the process. Uh, Selecting our project was no easy task either. We each had a couple of ideas to talk to each other about and see what our pros and cons would be for each project and how it could benefit the group as a whole. Scheduling conflicts lastly, since it's our final semester as a group, each member of the group all have different schedules ranging from work, other classes that are being taken, and trips, but we are able to work through all our issues together to make sure we can make the senior design possible and be able to present at the end of the semester.
So for this presentation, I will be comparing sensors, going over the schematic, going over some goals and objectives, and technology used. Raf and Berkai will both be going over software design. Raf will focus on administrative content, whereas Berkai will focus more on comparison and selection of software. Bedin and Kyle will both go over PCB design and comparison and selection of hardware. The goal of my plant is to allow users to more confidently tend to their plant. We do this by using our sensors to collect data and transfer it to our application where it will be analyzed. The data will then make the user aware of any shortcomings or notable plant conditions and make recommended actions. We want people that don't usually care for plants to be able to easily keep a plant alive.
Our hardware block diagram shows how the power source runs into the voltage regulator and then from there goes to the Bluetooth model and all of our other sensors as well as powering the MCU. The MCU will communicate through each component via various communication protocols. You can also see that we are using a solar cell to keep our power source charged at all times, which will be managed through an integrated circuit. All of this is connected then to our application in order to read the data from our device via Bluetooth.
For our light sensor, we went with the Adafruit VEML7700. As you can see from our table, we have researched other components that could potentially do the job. The reason we went with the VEML7700 was that despite its low budget, it could record lux values up to 120,000 lux. Some research determined that the average lux value on a hot day at noon could be upwards of 100,000 lux. Being the only one from our selection that could reach this range, we ended up choosing it, as plants could very well be outside or indoors near a window. It is very realistic that the lux value could be that high. Other benefits that were important to us were the temperature range and communication protocol. Almost every sensor had a good enough range of temperature as seen below the table, and communication protocol that we would like to use. I2C is extremely easy to integrate into our project, and overall we are happy with our selection in the light sensor.
In this temperature and humidity section, we will detail the sensors we've chosen and explain the reasoning for our selection. When comparing the DHD11 sensor with the DHD22 sensor, we ended up choosing the DHD22 sensor for its more enhanced features. In terms of communication, the DHD22 stands out for its more uncomplicated communication protocol, which promotes efficient data exchange and adaptability in handling variations in outdoor temperature. Our decision to utilize the DHD22 is grounded in its capability to provide accurate readings, paired with the responsiveness to varying environmental conditions.
Here we have the moisture sensors that were considered for this design. Some factors that we looked at were the input voltage, the input current, power consumption, corrosion resistance, accuracy, and of course cost. We selected the capacitive moisture sensor primarily for its corrosion resistance. The sensor is comprised of one copper plate as the positive electrode and a ground plate as the negative electrode, encased in a protective material. This design helps protect the sensitive electrodes from environmental factors like moisture and corrosion, making the sensor more robust and durable. The protective material encases the electrodes, acts as a dielectric and insulator. It isolates the electrodes from each other and prevents moisture from bridging the gap between them. This further protects the sensor from short circuits and electrical issues related to moisture exposure. Some other aspects are it contains a far smaller input voltage range than the IC station moisture sensor, which is important because it allows our components to operate optimally in the same range without large voltage spikes or noise. Another aspect was the current, as it had the smallest operating voltage out of the three. This will allow our sensor to fit within our criteria of being energy efficient and consuming the least amount of power by draining the power source at a much slower capacity than the other choices we considered. Last but not least, the capacitive sensor doesn't require an additional module to connect it to the MCU, unlike the other two. This will save a lot of space on the PCB and make the connection process simpler and smoother. This is done through a 555 timer that produces a voltage which is equal to the capacitor inserted into the soil. The voltage is measured with an analog to digital converted that can be interpreted as the amount of moisture in the soil sample. The downside is that it is the second biggest in terms of size, although we believe that the built-in corrosion resistance and not needing an additional module makes up for it. To power our system, we looked at 4 different batteries: lithium cobalt oxide, lithium ion, nickel cadmium, and lithium polymer. We looked at factors such as rechargeability, cost, energy density, coulombic efficiency, and life cycles. For this table, it seems as though all the specifications are relatively similar. However, we believe the lithium polymer would be most suitable for our project. We mainly looked at its advantages in an environmental setting. It possesses the second highest in energy density, and the batteries often come in lightweight and slim form factors. This makes it easy to integrate into the system without adding excessive bulk weight. Additionally, lithium polymers have a solid or gel-like polymer electrolyte that is less prone to leakage than the liquid electrolytes used in the more popular lithium-ion batteries. This reduced risk of leakage makes lithium polymer very suitable where leakage could be problematic, especially in heated environments. Although it is one of the more higher costing batteries, we believe it is worth the trade-off when we are dealing with environments where water and debris could potentially short-circuit our system. For our design, we chose the TP4056 circuit, which is an integrated circuit used for managing the interaction between a solar panel and a lithium battery. This integrated circuit serves as a charge controller, regulating the charging process and safeguarding the battery from potential overcharging and over-discharging issues. The solar panel exposed to sunlight generates DC voltage, which is then directed to the TP4056 input pins. Simultaneously, the lithium battery in need of charging is connected to the TP4056 output terminals. The TP4056 monitors the battery's state of charge and voltage, ensuring that it receives the correct charging current and voltage, all while adhering to a multi-stage charging algorithm. It prevents overcharging by reducing the charging current as the battery voltage approaches its maximum level and may switch to a maintenance charge once the battery reaches full capacity. Our advanced goal was to incorporate a solar panel to keep the battery charged so that we could eliminate the need for a USB-C charging port, since a charging port will create a weak spot on our device that could potentially allow water or debris from the environment to damage its circuitry. We are using a 6-volt, 1-watt solar panel for our system, which will convert sunlight to electrical energy, powering the TP4056, which subsequently charges the 3.7-volt lithium polymer battery. This solar-powered configuration enables the system to function autonomously, relying on renewable energy for its operations. So for the microcontrollers that we considered for this project design, we wanted to prioritize processing speed and Wi-Fi/Bluetooth capabilities, but at the same time, have familiarization in terms of software and user-friendliness. We wanted to budget our costs into making sure we get a high-quality MCU, so we were willing to budget around it. We took a look at various MCUs and selected the ESP32S3 Mini. The one we selected came in at $6.49, and we believe it is a complete package in terms of communication protocols, speed, input-output pins, power consumption, memory, and Wi-Fi/Bluetooth. It is a compact and versatile MCU with an operating voltage of 3 to 3.6 volts, which provides the main protocols we need, such as UART, SPI, and I2C. Compared to the other MCUs, the ESP32S3 is the fastest, which works at a clock speeds of up to 240 MHz. It contains built-in Wi-Fi and Bluetooth modules, and this is perfect for our project because we can utilize its Bluetooth low energy to maintain connections and data transfers.
I'm going to be explaining a little bit of the technology we used behind this project. For our MCU selection, we did need to select an MCU that could support I2C, have a Bluetooth communication protocol, and could accept analog. Most MCUs do I2C and analog communication. That wasn't a big deal. But the Bluetooth communication was something that we needed to search for. We have moisture sensors, a light sensor, and a humidity and temperature sensor, which needs to be connected to the MCU all at once. There's also a combination of research technologies that we are embedding into this project. We have a solar battery charger, a battery, some voltage regulators, Bluetooth communication as mentioned before, ADC, I2C, Bluetooth communication protocols, some switches, buttons, connectors, and a USB to UART to flash the code into the MCU. Our project revolves around the idea of data collection. So since each sensor will be collecting data and feeding it to the MCU, all technology must communicate properly in order to ensure that the data does not get lost or damaged in any way. I talked a little bit about the technology that we used in the last slide. Here's the schematic that will show you how we integrated everything together into a circuit that will provide everything that we need. I'd say a challenge we faced while designing the circuit was learning how to use the enable switch or the reset switch, because depending on whether or not you want a reset button or not, it will change the circuit that you need to connect to the pin.
For our PCB design, our goal was to create a board that was compact and fit within our set of parameters. It was also important that each component was positioned in a way that gave us plenty of space to solder them when we were ready to get to that step. We also tried to place each component and peripheral that were directly connected to each other in places that the traces could be easily made to reduce the number of vias in our board. The PCB layout was determined after first placing the MCU down. Since it has an antenna for Bluetooth connectivity, it must be placed in a specific orientation in order to work to the best of its capabilities. If the MCU were placed incorrectly, the Bluetooth connection would suffer and cause a problem with the connection to our application. So as you can see in the picture here, the MCU needs to be placed in a location where the antenna has nothing under it. So we place it at the top corner of our PCB to ensure a proper connection. As for the other peripherals, the light sensor was placed on the top of our PCB so that it would be exposed to as much light as possible. Temperature and humidity sensor was placed in the middle only for spacing purposes. The moisture sensor was placed at the bottom so that it could be pushed into the soil. And the USB to UART, as well as the buttons, were placed on the sides for easy access. And for all the resistors, capacitors, and inductors, we chose size 0805 and also placed them in positions close to whichever of the peripherals or chips they are a part of. The size of our PCB was determined by the size of our solar panel that we are using to keep our device's battery charged. So we required the PCB to be smaller than 110 millimeter by 60 millimeter. So the actual size of our PCB is approximately 87 millimeters by 57 millimeters. We decided to make it this footprint so that we had a small and compact device that would also look nice as a complete product. And to solder our board, there were two potential choices. We could either solder everything by hand using a spool of solder and a soldering iron, or solder everything using the reflow method, which utilizes a solder paste, a stencil, and some form of heat to cause the paste to melt and form a connection. We thought it'd be most beneficial to do the reflow soldering in order to make it quicker and easier to solder everything. In order to flash code into our MCU, our PCB required the use of both a reset button and a boot button. as well as a USB to UART connector to do the actual flashing. In order to do this, we refer to the ESP32S3 mini datasheet to find the schematic of peripherals and then added those needed to our PCB. The schematic can be seen in the image to the left, and our PCB can be seen on the right. The buttons and USB to UART connector on our schematic can be seen in the slides above. One of the challenges of assembling our first PCB was that after applying the solder paste with the use of a stencil, some of the contacts on a voltage regulator were connected and had to be scraped off in order to ensure a proper connection after the heat was applied. We also had an issue with the position of our MCU since the Bluetooth antenna was not in the best position due to the PCB being underneath it. After that, we also determined that we had an issue with our input voltage after doing some testing, which led us to not be able to flash any code to our MCU. Following that, we determined our original schematic had an issue and made the necessary changes seen in the slides above to our schematic and PCB.
Let's now focus on our core engineering specifications. In the software data analysis specification, the program specifies desired results based on a chosen plant species, guiding users towards actionable recommendations. In the plant species specification, our program demonstrates recommendations for 3 specific plants, suggesting optimal setting adjustments for each. In the data transmission specification, we'll detail how data is collected and then sent via Bluetooth to the users for analysis. These specifications, which are software analysis, plant interactions, and data transmission, are our main engineering specifications. Turning to the software tools, let's discuss the specific software our group will use for this project. Regarding user experience, we prioritize a design that's user-friendly and intuitive, ensuring that navigating our platform remains straightforward. When discussing microcontroller interactions, our software is designed to interface with the MCU, optimizing data flow and system performance. From a connectivity standpoint, our tools facilitate the integration of plant care device with a web application via Bluetooth, enhancing real-time user engagement. To sum it up, our focus areas, which are user-centric design, MCU interfacing, and Bluetooth connectivity, are the core components of our software approach. Let's now look into the primary functionalities of our MyPlan application, as illustrated by this flow diagram. First action the application triggers is Start MyPlan Application, which sets the stage for all subsequent processes. The user interaction bubble represents the platform's main interface where users can select their plant. Simultaneously, the application actively engages with the read sensor values and initial sensors functionalities, ensuring real-time data acquisition and readiness of all sensors. These functionalities illustrate the structured process a user follows within our application. On this slide, we'll break down the MyPlan approach to guiding users with plant care notifications as represented in the diagram. At its core, the MyPlan dashboard acts as a comprehensive hub orchestrating the delivery of tailored advice and feedback to users. From the central foundation, we have the alert system designed to give users immediate and actionable plant care adjustment tips. The notifications arm emphasizes regular updates with care tips aligned to the plant's current state and environmental conditions. This structure aims to provide users with timely and relevant advice for optimal plant care. This slide presents the workflow of our sensor alert system, as depicted in the diagram. At the check sensor threshold step, the system cross-references the current sensor readings with set criteria to identify errors. In the soil moisture specification, the soil moisture sensor assesses the soil's water content, alerting users if values deviate from the ideal range. In the lighting specification, the lighting sensor actively measures ambient light conditions to ensure plants are under the right illumination. For the humidity specification, the humidity sensor tracks the surrounding air moisture, completing our detailed sensor check to optimize plant health.
Some of our stretch goals as a group for our MyPlant project will consist of using a dynamic plant species database. This will replace our hard-coded plant species database and allow us to make it adaptable to fetch information on new plant species in real time. This could offer a wider range of plant recommendations for our different users. Having individual plant accounts would also be beneficial, since it would mean to have dedicated accounts for each plant in the user's collection that they might have. This would have our users be able to monitor at real time multiple unique plants that they might have. Our last stretch goal would be able to incorporate more sensors that we weren't able to incorporate in the senior design project for our final cut. This would be able to collect more information and provide more precise recommendations. This image right here is our current estimated project budget. We say estimated since we are still dealing with different environments. There could be a lot of things that might go wrong in the process. We would like to be around our estimated costs, but we know we might some have additional costs along the way. This is our Excel sheet we created before the semester began to be able to keep everyone on the same page due to our schedules, and to have us alongside the project to make sure no one was getting left behind and everyone knew their roles. This will allow us to be separate in teams depending on the work needed. While this hasn't been updated to the date due to some recent changes, this is our progress chart as of recent that we would like to begin to follow more thoroughly throughout the semester.